In this particular video, I want us to talk about gravitational fields, and this is a topic in CIE 9702 Physics. We are going to discuss what are the key topics, what are the main areas that are going to be covered in that particular topic. Then thereafter we shall look at the past papers. So one of the areas that you really need to understand is the definition of what we call gravitational fields. And gravitational field is going to be defined as a region. This is going to be defined as a region where a force is experienced. So we're going to say gravitational field is the region of space around a mass where another mass experiences a force of attraction. So something that you ought to remember when we are talking about gravitational field is that these fields, they are attractive. So once you've understood that definition of gravitational field, another area that you may be asked is the area of defining what we mean by gravitational field strength. We have gravitational field strength is defined as force per unit area. So in A-level physics, if you are told to define gravitational field, you're going to say is a region of space around a mass where another mass experiences a force of attraction, and gravitational field strength is force per unit mass, force per unit mass, which is well stipulated here. So gravity is F over the mass. The Earth's gravitational field, we are going to see that the Earth's gravitational field is radial, meaning it's directed toward the center, and as you move away from the Earth, the fields are going to spread. And when that is the case, when the fields are much apart from each other, the gravitational the strength of the field becomes weaker as you move away. So you can see there's, as you extend this, they're going to be quite apart. And in that way, we're going to say when the fields are much apart, they are going to be weak. And something that you notice, these fields are directed towards the center of the Earth. So the increased separation of the field communicates the reduced strength of the fields. And the direction that we are having here indicate that if you place a mass test or a test mass, if you place a very small mass here or a mass that is going to be tested, you need to realize that the mass will be attracted towards the Earth because the Earth is bigger and is going to have a stronger force of attraction. So this arrow indicates this test mass is going to be moving in this particular direction. So basically, that is what you need to understand as far as fields is concerned. Another aspect that you are going to learn in A-level physics is the concept of Newton's law of gravitation. So we're going to talk about Newton's law of gravitation, and in this case, you need to know how Newton's law of gravitation states. It states that any 2 point masses attract each other. The force of attraction is proportional to the product of the two masses and inversely proportional to the square of the distance separating them. So which means that force is proportional to the product of the masses. So you take mass 1, mass of this object, times the mass of this object. Then in that way, over the square of the distance between the two masses. So if we introduce the constant of proportionality, which is going to be the universal gravitational constant, we are going to have force F is equals to the constant of proportionality, which is the universal gravitational constant, times the mass 1 times mass 2 over r squared. So this formula is used when you are trying to work out, or you are trying to find the force of attraction between two masses. And this can represent the force of attraction between a planet like Earth and another object, which is maybe a moon or a satellite. So you can be able to use that. And you need to understand and remember that the constant G is the universal gravitational constant, which is 6.67 times 10 raised power negative 11 Newton per meter square, and Newton meter square per kg squared. So you need to remember how you can be able to use that. So, and you need also to understand the definition of a point mass. What's this point mass are we talking about? A point mass is a uniform sphere of uniform density, and it's assumed that the mass is concentrated at its particular center. So you need to have that understanding that it's assumed that this object here, the masses are concentrated at the center. So when you are using the radius, it should be from the center of the masses or the object in question. The next part that we are going to also look at this point is circular orbit in gravitational fields. That's another area of interest, another area that you ought to have an idea about, because you're going to be asked to answer a question on that. Now, circular orbits in gravitational fields, yeah, just highlight it so that you can be able to see it properly here. Yeah, circular orbits in gravitational fields. Now, for instance, satellite in stable circular orbit has the gravitational force providing the centripetal force. If we have a planet like, for instance, Earth, and then we have a satellite that is orbiting this particular planet, yeah, we have satellite here that is orbiting. Now, the force that is keeping this satellite to move in the circular path is basically gravitational force, which is going to be equivalent to mv squared over r. Of course, we've discussed that in centripetal acceleration, and that is the area where we discussed about circular motion. So whatever that is keeping this in a circular path is basically centripetal force. So if we have said that the force of attraction between two masses which are separated by a distance r is gm1 times m2, then if we are going to talk about a planet of mass m and a satellite of small m, then the force of attraction between these two objects is going to be F is equals to gm small m, meaning that mass of the planet times the mass of the satellite over the radius of this particular orbit, and the radius is this radius r that we are trying to refer at this given point. So, but this force of attraction is equivalent to the centripetal force, which is given by mv squared over r. So basically, if you are going to cancel this mass and rearrange this formula, if you cancel this mass of the satellite or that object that is orbiting a planet and this mass, you realize that the orbital speed is going to be v is equals to square root of gm over r. And if you can be able to write that in terms of the periodic time, because we know v is equals to 2 pi over r, 2 pi r over t, periodic time is the time taken for an object to orbit a planet. Now, in this case, if we try to rearrange this, then we can be able to say, if you substitute v with 2 pi r over t, we are going to have t squared is equals to 4r cubed over gm. And we can be able to make t, which is the periodic time, the subject of the formula. And in that case, you are going to realize that we shall have t squared is equals to 4 pi over gm r cubed. Why are we having r cubed? Because r times r squared is going to give us the r cubed here. And now this is what we call Kepler's third law. Kepler's third law, which try to show the relationship that which is a relation which indicates. So Kepler's third law is trying to indicate or show that the square of the orbital period is proportional to the cube of the orbital radius. If we try to use also the angular speed, we know that angular speed is 2 pi over t, which will mean that if we try to replace that omega into the formula that we were having, we can be able to have our equation becoming this, and making m the subject of the formula at that given point can enable us get the mass of a planet. So if you want to find the mass of a planet, you are going to use angular speed squared times the cube of the radius divided by the universal gravitational constant. In this particular example that we are given here, we are told that the orbital radius and orbital period of Io is one of the moon in Jupiter, and we are given the orbital period radius rather to be 4.2 times 10 raised to power 8, and the orbital period is 42 hours. We are supposed to determine the mass of Jupiter. Of course, we are going to use the formula mass is equals to omega square r radius cubed divided by the constant universal gravitational constant. So for us to be able to find and work out this, we are going to use the formula orbital speed is 2 pi r over the time period. Basically, in this particular question, what I've just done, I've used this particular formula that orbital speed is 2 pi r over time period, in order for me to work out the speed at which that particular satellite, which was the moon, was orbiting around. So I've used that particular formula in order to work it out. So I got 1.75 times 10 raised to power 4 meters per second. So once I've gotten this, I can be able to go ahead and work out what? Work out the mass of Jupiter, because I can as well use mass is equals to the radius times the orbital speed squared divided by the universal gravitational constant, which is 6.67 times 10 raised to power negative 11. So I use this formula. Of course, I've tried to derive that formula here so that you can see where I obtained that particular formula from. Then I've substituted here. Whatever we have is the orbital period squared divided by g, and if you work it out, you're going to get 1.95 times 10 raised power 27 kg. That's the mass of that particular planet. Another method that we can be able to use is, or determining the mass of these planets, is the use of this particular formula we derived here. Mass is equals to omega squared r cubed, radius of the orbit divided by the universal gravitational constant. Then, but we don't have omega, then it means that we can be able to use the period, because already we were told the period was 42, in this particular case 42 hours. Then I'm going to use that 2 pi over t, then 2 pi over t. Time was hours, so I have to multiply 42 times 3600, and now omega is 4.16 times 10 raised power negative 5 radians per second. Then we can now apply it into this formula so that we can be able to get the mass of Jupiter to be 1.95 times 10 raised power 27 kg. Just same thing we had gotten here in order to work it out. You need also to understand the concept of geostationary orbit. A geostationary orbit is a special type of orbit, and this orbit is called geostationary because of specific properties that it has. And if we have a satellite that is going around this type of special orbit, that satellite is called geostationary satellite. And this type of satellite is observed to be still. It's observed not to be moving at any given point. And the reason as to why it's not moving is because of these properties that we are mentioning here. The geostationary orbit has the same orbital period as that of the Earth. The Earth takes 24 hours to rotate in its particular axis. 24 hours to rotate. So in this orbit, also that geosatellite takes 24 hours. So meaning as the Earth moves, the geosatellite also rotates. In the process of that particular rotation, then it's observed that that satellite is not moving. It orbits from west to east in the same direction as the Earth's rotation. So the orbit is directly above also the equator. So in this case, because of these three properties that I've mentioned here, this geosatellite is observed not to be moving. And the reason as to why this is the case is because some applications don't require antennae, right? So due to that antenna orientation, in order to keep it static at one given point, then this application of geostationary satellite comes in, and they are used as in telecommunication, they are used in television broadcasting, and also weather monitoring satellites. Another concept that you shall be looking at in this particular A-level physics, especially in gravitational fields, is the gravitational field strength. And we are going to use the concept of force is equals to mass 1 times mass 2 divided by the radius squared. If two objects are separated by a distance, then the force of attraction is that. And this force of attraction is basically equal to mass times gravity, because we say that the force that keep objects to move in orbit or get attracted to the Earth is the gravitational force, and the strength, that gravitational force is equal to mass times gravity, so which is mg, meaning that mg is equal to g mass times the mass of the planet times the mass of the object over r squared. So meaning that m and this m cancelling out, you are going to remain with gravitational field strength is equal to the universal gravitational constant times the mass of the planet divided by the radius squared. So which means that the mass that is being attracted by a planet has got no effect, has no impact in the gravitational field strength. Gravitational field strength depend on the radius and the mass of the planet in this case. So if you want to work out the gravitational fields at a given point on the Earth, you are going to use this particular formula, which we have said that G is equals to gravitational field strength is equals to the mass of that planet divided by the radius squared, which is the distance that is going to separate those two objects. So in this case, we can be able to approximate the value of the gravitational field strength of this particular question. So until next time, we shall be looking at part 2 of this particular topic. If you're new to ProfLearn YouTube channel, consider subscribing so that anytime I'm going to upload more tutorials, you'll be notified. And I would like you to check in the description, we shall be having a link that is going to take you straight to our Patreon page, where you can be able to access these notes that you can see here, so that you can be able to download them in the process of preparing for your exam. Good luck, all the best, see you in the next tutorial.